Hello everybody and welcome back. Today we will talk about longitudinal waves. We knew previously that a simple harmonic motion is the wave in its simplest forms. Longitudinal waves is one of the simple harmonic motions. The longitudinal waves are called so because they are simple harmonic motions in a horizontal way, in a longitudinal way. That's why they're called longitudinal waves. An example for these waves is like a mass attached to a spring, and this spring is attached to a wall, and the mass is pulled in order to move right and left on both sides of its equilibrium position. So this is a kind of a longitudinal wave. We have to know something. If we draw a graph for a longitudinal wave or a simple harmonic motion wave for this spring, we will find that first the spring with a mass was found here in its rest position, and then it moves away like that, moves a little bit more during that side, then it returns again. So if you track the motion of the object as if this is the rest position, so the mass was found originally here, it was pulled to this side. So what will happen is the object moves like that, and then it returns again to the equilibrium position. Sorry, it's flipped. Like that. So it moves right and left on both sides of the equilibrium position. I said if we track the motion of the object this way, we'll find that it forms kind of a curve. So if this is the horizontal which the object is moving on, and this is the path of motion, this curve here, we can see that we have an axis and there's a curve. This curve here is called the sine curve. So if any motion was tracked and it formed a sine curve, it shall indicate that this motion is a simple harmonic motion. And since the longitudinal wave is a kind of a simple harmonic motion, it has the sine curve. So what's the sine curve? Here's a little bit of trigonometry. Let's say we have the x-axis and the y-axis. There is something called the unit circle. The unit circle is a circle where its radius is 1 unit length. So on the positive x it's 1, negative x is -1, on the y dash is -1, and on the positive it's y. So if we have a circle like that, and here of course the axis makes 90 degrees here. So the sine of this circle is the reading of the y-axis, and the cosine is the reading of the x-axis. So if I want the sine of the angle 90, the sine of the angle 90 is 1, and the sine of the angle 180 is 0, because the reading of the y-axis here is 0. What about the sine of 270? It will be -1, and the sine of 360 is 0. So the sine curve is drawing the function fx, which equals sine x. So y equals sine x. Now we know sine 90 equals 1, and sine 0 degrees equals what? Here, the reading of the y-axis, no, there's no y-axis reading, so the y-axis reading is 0, and 180 is 0, and so on. We want to graph this function. Here how we get the curve. So we put readings of angles. Here we have 0 degree, here we have 90 degree, here we have 80 degrees, 180 degrees, 270 degrees, and so on. And here we have 1, like that. So we want to graph the sine curve. Sine 0 equals 0, here's our first point. Sine 90 degree equals 1. Sine 180 equals 0. Sine 180 equals 0. Sine 270 equals -1. Sine 360 equals 0. If we connect the points together, we will have the sine curve. Here we can notice that it's very simple to the one forming the simple harmonic motion, except that it's flipped 90 clockwise. So if we flip this like that, we will find the track of the motion of the object on both sides of its equilibrium position, which is represented here by the x-axis. And the positive amplitude is represented by the y part, and the negative amplitude is represented by the y dash part. That's what a sine curve means. So the sine curve is the property which distinguishes the simple harmonic motion. Now there's another thing that we want to talk about, which is called compressions and rarefactions. Now we knew the property which distinguishes the simple harmonic motion, which is the sine curve. Now compressions and rarefactions are the two properties which distinguish the longitudinal waves from other waves. So if you have a mass like that and it's attached to two strings, this one is long and this is short, and this is its equilibrium position, and we pull this mass to the right. What will happen is this part of the spring here on the right will be compressed a little bit on a part of it. So the object will be like that. Let's say the object will be here, and we'll have this part compressed and the other part of the spring is relaxed. And here we'll have this one so stretched. This part, which was compressed, is called a compression. So if we want to move this mass from this position to the other side, to be here, so we move it to the left, what will happen to this part is it will be relaxed a lot. It won't return to its normal position, but the gaps between the parts of the spring will increase more, and this part of the spring will be compressed. So the object will look like that. So this part of the spring will be very compressed, and that one will be very relaxed like that, and the other part will be normal. So this very relaxed part is called a rarefaction. A rarefaction. If this action is repeated twice or thrice, we will notice that some parts of the spring will have a very compressed parts, and other parts will be very relaxed. So this is called a longitudinal wave because it contains compressions and rarefactions. These compressions and rarefactions are formed because the wave spread along the direction of movement. The wave spreads along the direction of movement, or in other words, it spreads horizontally on a horizontal way, right and left, or in a longitudinal wave, or in a longitudinal way, and that's why it's called a longitudinal wave. So this is it for today. We knew what a longitudinal wave is, and the next time we will talk about another type of a simple harmonic motion, which are called transverse waves, and we'll know why they are called transverse waves. And this is it for today, and until the next time, I thank you for watching and see you.